Welcome to Coding Scientist. Let's build upon the transformer architecture with TensorFlow and Keras. TensorFlow and Keras, your building blocks. TensorFlow, with its high-level API Keras, is like the set of high-quality tools and materials you need to start painting. It simplifies building and training complex models. Step 1. Setting up your environment. Before diving into code, ensure you have TensorFlow installed in your Python environment. Pip install TensorFlow. Step 2. The encoder and decoder layers. The transformer model consists of encoders and decoders. Think of encoders as scribes, absorbing information, and decoders as orators, producing meaningful language. The encoder layer, following piece of code, defines a transformer encoder layer using TensorFlow and Keras, which are powerful tools for building neural networks. Let's break the code down. Import statements. Import TensorFlow as TF from TensorFlow.Keras.layers. Import multi-head attention, layer normalization, dense. Here, we import TensorFlow and specific layers from Keras needed for building the encoder layer. These layers include multi-head attention for handling the attention mechanism, layer normalization for stabilizing the neural network, and dense for fully connected layers. Defining the transformer encoder layer class. Class transformer encoder layer, tf.keras.layers, layer. This line begins the definition of the transformer encoder layer class, which inherits from TensorFlow's layer class. This custom layer will form one part of the transformer model. Initialization method, __init _def_init_self, d_model, number_heads, dff, rate equals 0.1 super, transformer encoder layer, self, ._init_. The __init__ method initializes the encoder layer. It takes several parameters. D_model, the dimensionality of the input and output of the layer. Number_heads, the number of heads in the multi-head attention mechanism. DFF, the dimensionality of the inner layer in the feed-forward network. Rate, the dropout rate used for regularization. Multi-head attention and feed-forward network. Self.ma equals multi-head attention, number_heads, D_model, self.ffn equals tf.keras, sequential, dense, DFF, activation equals relu, dense, D_model. Self.ma equals multi-head attention, number_heads, D_model. The encoder layer consists of a multi-head attention mechanism and a feed-forward neural network. Self.ma is an instance of multi-head attention, and self.ffn is a simple two-layer feed-forward network with a ReLU activation in between. F.ffn equals tf.keras, sequential, dense, DFF, activation equals relu, dense, D_model. Layer normalization and dropout. Self.layernorm1 equals layer normalization, epsilon equals 1e6, self.layernorm2 equals layer normalization, epsilon equals 1e6, self.dropout1 equals tf.keras.layers, dropout, rate, self.dropout2 equals tf.keras.layers, dropout, rate. These lines of code create instances of layer normalization and dropout layers. Layer normalization helps in stabilizing the output of each layer, and dropout prevents overfitting. Attention and feed-forward operations. Attention_output equals self.ma, x, attention_output equals self.dropout1, attention_output, training equals training, out1 equals self.layernorm1, x plus attention_output. Here, the layer processes its input x through the multi-head attention mechanism, applies dropout, and then layer normalization. It's followed by the feed-forward network operation and another round of dropout and normalization. Decoder layer. The transformer decoder is an essential part of the transformer model, often used in tasks like machine translation, text generation, and more. Let's break down the parts of the code that are new. Attention layers, two multi-head attention layers, MA1 and MA2, are defined. MA1 is used for self-attention within the decoder, and MA2 is used for attention over the encoder's output. The feed-forward network, FFN, follows a similar structure to the encoder. The call method, def call, self, x, enc_output, training, look_ahead_mask, padding_mask. This method is where the layer's operations are defined. It takes additional parameters compared to the encoder. Enc_output, output from the encoder. Look_ahead_mask, to mask future tokens in a sequence, for self-attention. Padding_mask, to mask padded positions, for encoder-decoder attention. Attention and feed-forward operations, attention 1, attention_weights_block 1 equals self.ma1, x, look_ahead_mask, attention 2, attention_weights_block 2 equals self.ma2, enc_output, out 1, padding_mask. The decoder processes its input through two multi-head attention layers. The first one, attention 1, is self-attention with a look-ahead mask, and the second one, attention 2, focuses on the encoder's output. This is followed by the feed-forward network. Each step involves dropout and normalization. Step 3, assembling the transformer. Think of this step as assembling your orchestra. Each encoder and decoder layer is an instrument, and you're arranging them to create harmony. The complete set of code to build full transformer model is available on our GitHub, or you may reach us at www.codingscientist.com. Training the model. With the transformer model assembled, it's time to train it. This process is like teaching the orchestra to play a symphony, where the symphony is the task you want your model to perform. Example, language translation, text generation. Preparing the data. Data preparation involves collecting a large dataset of text and processing it into a format suitable for training. TensorFlow's data API can be used for this purpose. Training loop for epoch in range, epochs for batch, inp, tar, in enumerate, dataset. However, we will explore how to leverage existing LLMs by using transfer learning. Implementing transfer learning with Hugging Face. Transfer learning in the context of LLMs is akin to an apprentice learning from a master craftsman. Instead of starting from scratch, you leverage a pre-trained model and fine-tune it for your specific task. Hugging Face provides an extensive library of pre-trained models which can be fine-tuned for various NLP tasks. Setting up Hugging Face transformers. First, you need to install the Hugging Face transformers library, pip install transformer. Loading a pre-trained model, choose a pre-trained model from Hugging Face's Model Hub. For this example, let's use BERT-based a popular BERT model. From transformers import BERT tokenizer, tf BERT model tokenizer equals BERT tokenizer.from pre-trained, BERT-based model equals tf BERT model.from pre-trained, BERT-based. Preparing data for fine-tuning. Suppose you're fine-tuning the model for a sentiment analysis task. First, pre-process your data. #example sentences equals, I love this product, this is a bad product. #tokenized sentences inputs equals tokenizer, sentences, padding equals true, truncation equals true, return_tensors equals tf. We have to use BERT tokenizer to ensure everything is tokenized and padded exactly as BERT likes. Fine-tuning the model now, you can add a classification layer on top of the pre-trained model and fine-tune it. Code for fine-tuning can be downloaded from our GitHub, or you may reach us at www.codingscientist.com. Testing the fine-tuned model. Finally, test the fine-tuned model on new sentences. You may find the below code in our GitHub or reach us at www.codingscientist.com. Stay tuned and keep learning. Subscribe to our YouTube channel www.codingscientist.com.